In this video, we're finally going to get to what you've all been waiting for, the lecture of the lecture set where we finally discuss hand calculation. I'm just kidding, but this is an important component, again, of what we're doing, so let's jump right into it. In this lecture video, we're going to discuss measures of central tendency. So central tendency just means the middle. And this is going to be in contrast to a future lecture video where we discuss measures of variability or spread, how spread out things are. So we're going to have two kinds of statistical measures of where the middle are and measures of how spread out the data are. And this lecture video is going to discuss the measures in the middle. Now there's some basic notation that you should be aware of as we get going. Throughout this course, you're going to see some math notation that can look intimidating, but this can really be helpful if you get the hang of it. Hopefully, this is going to help you get the hang of it a little bit. Ultimately, think of math as learning literally another language, just like learning Spanish or German or Russian or Chinese. It involves some level of practice to get the hang of it. So if I'm learning Mandarin, I need to jump into it and practice the language. Same thing when learning math and equation notation. So give yourself some time. Don't feel like you should get it immediately, but also make sure that you consider taking the time. Ultimately, these math equations are ways that those in the know or mathematicians can write whole paragraphs of relationships in just a few short characters. And so we'll discuss how that happens. In some places, you'll even see me take a whole slide trying to write out something in a word, in words, and then you'll see a relatively short equation after it that just summarizes all of that using this notation. So the notation actually is very helpful, but again, it takes some time to learn and get the hang of. So if you're not someone who's already familiar with this, please do give it a little time. Consider making some flashcards or something so that you can get some practice. All right, the first is this Greek sigma, which stands for sum. That just means add everything up after it, and sometimes it has parentheses after it, so you'll add everything in the parentheses that come after this. So if you see sum and the letter x, then you'll add up all of the values that are in that x variable. Speaking of x, you'll see x's. You'll see y's, you'll see z's, you'll see a's, you'll see b's. All of these stand for different variables. So X might represent favorite color. Y might represent age. All of these things can represent different things. And I have to tell you, or the paper you're reading has to tell you what it represents. So don't feel silly that you don't know what X means. Somebody has to tell you what X means. I have to tell you X is the age, or something like that. And then whenever you see X, just think age. Now, when you see an X with a little I next to it, that indicates a specific data value. In this case, the data entry for the ith person or the ith entry. That sounds really fancy, but just think if I have 10 people, I might write X, and X represents age. I might write X with a little 2 next to it, and that stands for the age of the second person. I might write X with a little 5 next to it, and that stands for the age of the fifth person. So I is just a generic term for I don't know what person we're going to be talking about yet. And so X sub I represents the age of the ith person. And again, X just isn't age. It could be your favorite color. And you have to be told what it is in the context of a specific problem. So X represents a variable, and X sub I represents the entry of the ith entry, or the ith person typically, but sometimes it's the ith business or the ith school or the ith hospital or the ith floor or ward. So the ith entry in that variable. Oh, and I even have an example. How nice of me. So let's consider the what is this? Percentage increase in expenditure for 3 years before, during, and after the implementation of the ACA. So I think that's what, 2008, 9, and 10, or 9, 10, 11. So 2009, that'll be our first year. I equals 1, the first observation of the data point. 2010, The second year, I equals 2. 2011, that'd be the third observation of the data point, I equals 3. And then I would have x sub I, that's the ith entry. So the variable in general is x, that's the percentage increase. And then x sub I would represent the ith entry. Specifically, x sub 1 represents the first entry, or the first percentage increase, which is 6.7%. X sub 2 represents the second entry, or the second percentage increase, or percentage increase for the second year we're considering, 2010, which would be to 8.5%. And then x sub 3 would be the third entry, 8.1%. So in general, I could say x sub I, and you would understand I'm talking about one of those specific entries, or I could say x, and you'd understand that I'm talking about that whole column or that whole variable of percentage increase. And that's how we would use x versus x sub I differently. Those numbers, I think those numbers are percentage increases. I don't think that they're specifically related to the Affordable Care Act, if I remember correctly where I pulled those from. So I don't take these as gospel. They're just meant to be an example of how we use x sub I notation. All right, so little case n, this is the size of the sample. So how many individuals did you pull from the sample? So let's say I sampled 100 hospitals. Little n would equal 100. Now, what's interesting about this is that this notation, and most of the notation you're going to see in this class, is going to be regarding the sample. Because again, we don't have access to population level data almost always. So much so that I'm not even going to talk about population level calculations or notation. Outside of the fact that I do want to mention that the notation is slightly different for population. So instead of little n being the size of the sample, capital N tends to be the size of the population. Instead of little x representing percentage increase as a variable, sometimes we use capital X to represent the broader construct of percentage increase. So typically we use capital letters or Greek letters to represent population values or parameters, and we use lowercase to represent specific incidences of that or the sample. Lowercase n sample size. All right, so let's jump into calculating our first measure of central tendency, the mean. So the mean is kind of cool. Maybe you've heard of it before. It's kind of like the average. A lot of times when people say average, they mean the mean, if you'll forgive the phrase. Not all people know what the mean is. So think about a balance beam. Think about like a board. And I put on a whole bunch of, I don't know, marbles. What do people put on boards? I don't know. And then I put my finger underneath it. The mean would be the balance point of the board. So if I slid something around, I would have to move my finger to represent the new balance point. That's how the mean works. If I move data, the mean would move accordingly. So the mean represents the tipping point or the balance point of a data. And that's why, one of the reasons why it has a ton of fantastic theoretical properties. To calculate the mean, we simply add up, or sigma, we'll see the notation in a moment, the values, each of the values in the data set, so each of those x sub i's, or in aggregate, just x, and divide by how many values were in the data set, n, that's the size of the sample. And that's really it. So the formula is the sum of x sub I divided by n. I'll note, I guess I didn't mention this earlier, that on this sum, you'll see the bottom and the top. So this says, what specifically am I taking the sum of? And this says I'm taking the sum of everything in the parentheses, starting from 1 and going up to n. So n could be maybe 30 or 100 or 1,000. I start at 1 and I increase in increments of 1 all the way up to whatever that top value is. So the bottom and the top. So that's what it is, the starting number and the ending number. This little I equals says what number is going to change. So in this case, I is going to change and go from 1 to whatever that top number is. Let's say 1,000, a sample size of 1,000. So I'm going to look at each I starting from 1 and going up to 1,000, and I'm going to add all of those numbers together. So that's this sum notation here. Now, there is a new component of notation here on the left-hand side, x with a little line over it. This x with a little line over it is called x bar, and x bar represents the sample mean of the sample mean calculation. The population mean, again, tends to be either uppercase or Greek. In this case, it's a Greek letter, and it is a little u with a little line in front of it. That is the Greek letter mu. So if we use x bar, remember, we tend to use sample statistics. X bar is the statistic. And to estimate population parameters, mu is the parameter. All right, so let's try a couple examples. I'll try one just to show you how we calculate this through, and then I'm going to give you the opportunity to try one yourself where you can pause the video and then give it a shot. I encourage you, if you are looking at the notes, kind of set them aside so that you can give this a shot, just work it out by hand. Or I encourage you, that's if the examples are provided in your note set. You may not have that. So if they are, set that aside so you can get some practice. And if you're already feeling confident about this one, when I say I'll try it, just go on and pause the video there anyway. And that way you can practice working out two of these problems. In this class, I highly recommend going and reworking these problems in preparation for your homework, as your homework is graded for correctness. I'd love you to be able to put your best foot forward. So do take some time, get some practice, and see how you do. All right, so for the one I'll try, the average ER visits per day for the last week at one particular country hospital. We have these values here. And again, go on and pause the video if you want to try it yourself for calculating the mean. But this is one that I'll go on and work through. So my formula, the sum of x over n. So again, I'm adding up. I can read this formula. Truly, read it. Sum, add up all the x values. So I didn't really specify here, but there's only one variable we could be talking about, average number of ER visits per day. So sum up average number of ER visits per day, divide by how many I have. So that's how I break this formula down. Thinking through this, that just means I add all these up, then I divide by how many I have. So how many do I have? 1, 2, 3, 4, 5, 6, 7. Well, I guess the problem says the last week, so I probably could have put together 7. So I have 7 observations here. So I'm going to add up all the numbers on the top, divide by 7, and that gives me my sample mean. I'll round to 2 decimal places. My rule of thumb tends to be 4. I have actually had several contracts in the public health sphere where rounding to 2 decimal places led to drastic underestimates of program effectiveness. I'm going to do it here for convenience, but I mention that because I do want you to know that even small things like that can have an impact. So if you're dealing with, say, a percentage value, 0 point whatever, 0.5 representing 50%, so that 0.5 would be a proportion, I would highly recommend you got to 4 decimal places. In this case, because I'm dealing with whole number visits per day, an extra 2 decimal places I think covers it. But again, I have had professional instances where not going out to enough decimal places have led to incorrect program decisions. Not bad math, not even bad interpretation, but a bad decision about how many decimal places we take something out to. In the data analytics sphere, it's always best to let things go out to as many decimal places as possible. We do that on the programming side by using Excel, so that Excel and cells, so we reference cells directly, instead of having to retype something and getting bored, so we only type a couple of digits. We actually let Excel pull as many digits as Excel can possibly store into the calculation. So that is much, much, much more accurate. And again, there have been cases that I can speak to professionally. I won't, because I don't want to speak to the program specifically. But there are 2 that I'm thinking of right now that actually made incorrect program decisions because of misrounding their decimal place. Not even misrounding their decimal place. They didn't make a mathematical mistake. They just chose to round to 2 decimal places in a proportion when they should have gone to 4. And that going out to more decimal places would have made a not just, again, y'all, I can't specify this enough. I can't encourage this enough. This isn't like some weird math thing that somebody did and like, oh man, some mathematician got upset that it rounded to 0.0003 instead of 0.0004. No, a program decision was made that had a drastic impact. We're talking hundreds of thousands, if not millions of dollars, based on not a rounding error, but not going to enough digits, which ultimately led to an incorrect conclusion. All right. Anyway, in this class, we'll go to 2 unless it's a proportion, then I'll go to 4. So now, why don't you try one? So let me pull up the example. So this is daily net income from ER visits last week in thousands. So it's got a couple decimals, so it's a little harder than mine. But why don't you pause the video right now, go on and click pause. Truly, click pause, click it, and give this a shot, and then we'll go through it. Okay, coming back, hopefully you got the chance to work through this. I have x bar equals the sum of x over n. This is the same equation as before. Sum of x, I add up all the values, divide by how many I have. I still have 7 the last week, add them all up. I get about 12.64, hopefully, something in there. Now, I can say what's really important, especially if you're doing this by hand, is to give it a gut check. And ladies and gentlemen, one of the most important skills I can teach you in this class is the gut check. What is a gut check? A gut check just says, does that seem reasonable? And there's a couple of ways to do a gut check. First of all is to gut check against your professional experience. Y'all, if it seems unreasonable, that's a good indication that maybe it is. Maybe something's gone wrong. Now, it's important to realize that if data says something, maybe you're wrong. That's okay to be wrong, and it's okay. But if it seems unreasonable, it is worth looking into a little more. And I'm amazed, astounded, so disappointed, so saddened by how many people have really good ideas, have really good gut feelings, and don't feel comfortable fighting the data. And what I mean by fight the data is not you should disbelieve the data. What I mean is if it doesn't make sense, find out a little more about it. Now, if you find out more about it and everything's legit and you were just wrong, have the humility to say, oh, I'm sorry, I guess I was just wrong about that. But if the data say something that you think just doesn't really jive, it really disagrees with your experience, what I would encourage you to do is to go back and look at some of those things we talked about in the first video. First, check the calculation, make sure it's correct, and that's what we're about to talk about now. But also check, how was the sample collected? Was this an observational or experimental design? Like, is the interpretation you're assigning to this something I would agree with? And consider, maybe it was you were asking about smoking behavior and you went to a whole bunch of people in a smoke shop to ask about it. No numbers were miscalculated, but the interpretation that you're applying to that result, that 100% of people love smoking, doesn't seem to me to apply to our context, where you gathered a bunch of data on people outside of a smoke shop, and I work in a hospital, and our participant pools are not the same groups of people. Our populations are not the same groups. So gut check, such an important thing. So that's the first type of gut check, is gut check against your experience. And again, I don't want you to hear me say disbelieve the data, because I think data, ultimately, we should be able to specify ways in which we can be wrong and then collect data on it and then observe it and stick by it. That's part of what statistics and research is all about, is collecting data on things and learning from that. But just as often, I'll say, in my experience, have been cases where either we collected data in a slightly weird way or we made a slightly weird calculation, so that when a finding is truly unexpected, it's actually not that unexpected. It's just that we're explaining it in a slightly off way. And it could even be the interpretation of a statistic is slightly off. Oh, I thought you were talking about the increase of people, but you're talking about the percentage increase of people. I'll say we recently started a data analytics program here at UNA. We had a 6,000% increase. Is that right? 6,000? Yeah, that might be right. Or maybe it's 1,200. Over 1,000% increase in our student base. We were, in comparison to all the programs, way better. I think it was. I think it was less than 6,000. I think it was over 1,000. So let's just call it 1,000. How does that happen? Well, we started with 1 student, and we went and we added 10 more students that first year. Well, that is a 1,000% increase. Great. But that doesn't necessarily mean what you think it means. It doesn't mean our data analytics program is 1,000 times better than every other program. By no means. What does that actually tell us? It tells us it was a small program, it started from low numbers, and that we're growing. We're growing in a good direction, but that doesn't mean that we're putting everyone else to shame in a way that someone who didn't understand that interpretation may accidentally interpret that to show. So gut checks, again, look for, give yourself the grace to ask that question of the data. At least probe into it just a little bit. And if it turns out you're wrong, that's okay. But if it turns out you're right, you can save yourself, your company, your hospital, your medical practice an immense amount of time, an immense amount of money, and you can save your patients too. So I highly encourage you to follow that professional gut check. Another way to say that, extraordinary claims require extraordinary evidence. So data should be able to stand up to a little bit of scrutiny. Absolutely. It should be able to stand up to a ton of scrutiny. But I don't encourage that. I encourage you to, again, if it disagrees with your professional experience, just find out a little bit more about it. That's all I'm saying. All right. The second type of gut check is to compare the result to the numbers. Recall the interpretation of the mean, or that gut feeling of the mean. The mean is the balance point. So if I have a number up, the top number here is 56, 57, I guess. The bottom number is 24. Well, if I'm looking at 2 edges of a board, the balance point should be somewhere in the middle. So if my balance point isn't in between these, then that would indicate a problem with my data. In this particular case, 42 falls somewhere in between 57 and 24. It is higher on the 57 side. Is that reasonable? Well, maybe more of my data points are on that 57 side, 57, 56, 48, 45, 39. So there are some higher data points than just a couple of lower ones, 26, 24. So maybe that does, again, gut check makes sense. In this case, 12.64. What can happen, especially if you're doing this, sometimes people have a typo. Ladies and gentlemen, if you hand enter data, and many organizations and research places do, not all of them, it's not particularly good practice, but sometimes we do. In that particular case, it can be really important to make sure that you're gut checking your data against your expectation. If I'm looking at net income in thousands, if I see a 0 in here, I might not really believe that. In the same way, y'all, if I see 300 million in here, maybe I don't believe that. Maybe that's 2 records that got combined, where I had 1447.8. You know, maybe I just messed up in typing this in. Well, that would seem to be a potential typo, and I would need to go back and double check that data. So again, this value and comparing to these data values seem reasonable. The data values seem reasonable. So the conclusion seems reasonable. That's my gut check here. All right, the median. So while the mean represents the balance point of the data, and again, think about a balance point, the median represents the middle of the data set. And I tend to express this as X tilde with a little tilde on top, but that is not necessarily standard notation. I saw that in a textbook somewhere and I kind of liked it. But if you write an X bar, an X with a line on top, everybody knows that's the sample mean. If you write an X tilde, some people might know you're talking about the median, but that's not something that everyone is necessarily going to understand. So understand that. That's my notation. I saw it in a textbook. So at least one other person uses it. I kind of liked it, but it's not necessarily industry standard. I would say there is no necessarily industry standard notation for the median. So while the mean, again, represents the balance point, the median represents the middle. So again, think about a board with a whole bunch of things on it. If I'm balancing it on my finger and I move around the data and I move around the things that are sitting on it, I would have to move my finger to follow where those things are. The median is much more like the middle object. So unless I move enough things that the middle object changes, even if I slide some things in and out, as long as where the middle object stays the same, the median stays the same. So it literally is the middle of the data set, and it moves around a lot less often than the mean does, which is sometimes really good and sometimes not as good. So here, the biggest thing I want to point out is, as a component of the median, we line up all of the numbers in order, and then we find the middle. So that actually is going to be the first step of the calculation, is lining up all of the numbers in order before we find the middle. And I really, really do mean the middle number. So if we have 5 numbers, 1, 2, 3, 4, 5, the middle number is the third number. If we have 3 numbers, 1, 2, 3, the middle number is the second number. What you'll see here is that this is pretty easy with an odd value for the sample size, 1, 2, 3, the middle number is the second number. But if I have 4 with an even number, 1, 2, 3, 4, what's the middle number? Well, I have 4. There isn't necessarily a single middle number. So let's talk through that. So for an odd, again, think 3 data points. What we do is we calculate the number of data points, divide by 2, and round up. Always round up. In fact, this will always be a 0.5, so it'll always round up. In a future calculation, it won't always be a 0.5, but we still always round up. So we always go up, even if it's not mathematically appropriate. No, your grades do not function like this. In your grades, we round up appropriately. But here, we round up no matter what. So we calculate n over 2, round up. This is the position in the ordered data set. So think mentally just through 3 data points. Again, it's clear to see that the second one is the middle one. So if you just hold up, the number 3 on your fingers, you can count over 1, 2, 3, and you can clearly see that second finger is the middle one. So if we applied this formula, we would do 3 divided by 2, that's 1.5. We round up to 2, and it would indicate that the second data point is the one that we're interested in. Now, I should say the median is not 2. The median is whatever number is in that second data point. So I would go to the second data point, I'd treat it like a blank, and then the number that's in that second data point, that's the one that is the median. So that is for an odd value for the sample size. Oh man, I even have an example here. So this is with 5, at least it's with something different. So if I've got 5 numbers in my data set, I'd calculate 5 over 2, 2.5, round up to 3, and then I would go to the third number in the ordered data set. Remember that second bullet point, we line up all the numbers in order, so I'd go to the third number in the ordered data set. And again, it's that third number. The median isn't 3. Hear it with me. The median isn't 3. The median isn't 3. The median is whatever number is in the third position. So I'd go to the third position, and that number is the median. Now, for an even sample size, this is a little more tricky. We calculate n over 2, which for an even sample size is going to be a whole number. This gives us a position, and then we do this position and the next one up. So let's do a quick example here. Let's say we had 6 numbers. This would work with 4 numbers, our example earlier. 6 over 2 is 3, so that's the third position. And then we would say the median is between the third position and the next one up, which would be the number in the fourth position. Normally what we just do is we take the value of the third and the fourth numbers and we average them together. We take the mean of both of those, add them together, divide by 2. But technically the median is between these 2 numbers, and there are some different formulas for how to calculate that. Again, in this class, we'll just use the average between them. All right, let's work through examples, and I'll try 2. I'll try one with n is odd and one with n as even. So let's do this. This is an n as odd one. So first, don't forget the first step here, ER visits per day. I think this is the example we had last time. The first step is to order the data. So I put these in order from least to greatest. And then I use that n over 2 formula. I have 7 numbers, so I do 7 over 2. That gives me 3.5, round up to 4. So I go over 1, 2, 3, 4. The fourth position in the ordered data set. Here, the fourth position is the number 45. 45 is my median. And again, I want you to hear that the calculation is to find the position, but the number in the it's the number that's there. That is what the median is. All right, let's try this one more time. So we have the ordered data set. So I'm doing just the last 4 days so that I get an even number for our practice calculation. The previous calculation gives n over 2, 4 over 2 equals 2. Again, I take this and the next one, and I want you to look at this in our ordered data set. N over 2, the second position. If I look at this, 2 is kind of clearly not the middle. With 4 numbers, again, there's kind of this line in between, or maybe these 2 are the middle 2 numbers. So if I just go to the second one, that's not it. Remember, with even numbered data, we do this one and the next one, and it's kind of in the middle of these 2. That's what the median formula is saying, is it's in between the n over 2th one and the n over 2 plus 1th one, if you want to say it like that. So it's in between these middle 2 numbers. And so we take the average. We take 45 plus 56, the second and the third position, and divide by 2, and that gives us 50.5 as our median. All right, now it's your turn to try a couple. So go on and try this one. The median net ER income from the last 6 days. Go on and pause the video and give this one a shot. All right, coming back to this. Well, so first we order the data. We put all the data in order, and then we do n is even, so we do n over 2 and n over 2 plus 1. These are the 2 numbers, n over 2 and the next one up. So here, n is 1, 2, 3, 4, 5, 6. So 6 over 2 is 3, the third number in the data, and the fourth number in the data. Now, I want you to be careful here, because I don't want you to go to the original data set and say 1, 2, 3, 16.8, 1, 2, 3, 4, 7.2. That's not correct. Remember, the median is calculated using the ordered data set, so be careful here. I go 1, 2, 3, n over 2, 6 over 2 is 3, that's why I'm going 3. And then 1, 2, 3, 4. The next one up, plus 1 is mathematically how we say the next one up. 1, 2, 3, 4. And I'm looking at the average, or the mean, of 11.1 and 13.5. That's what gives me 12.6 as my median. All right, give it a shot. One more. Income from the last, I say 5 days here, but I only have 3 days of data. So why don't you go on and give this one a shot. Yes, so n equals 3. I guess that means we shouldn't trust my slides very much. I apologize about that. So n equals 3. I put these in order. That's important. I divide by 2. That gives me 1.5. Round up to 2. It is in the second position in the ordered data set. So note that I would have to order the data set first. It's currently not ordered. And once I put it in order, that second position is 13.5. All right, so moving on from the median, let's talk about quartiles. Now, quartiles are not necessarily measures of central tendency per se, but are directly related to the median. Typically, we look at 2 quartiles of interest, and these are the first and the third quartile. We denote, or the way in which we note or write down the first and third quartiles is Q sub 1, that's the first quartile, capital Q, and Q sub 3, that's the second quartile. Now, quartiles, think about like a quarter. If I have 1 quarter, I have 25 cents. So the first quarter is the 25th percentile. If I have 2 quarters, I have 50 cents. And if I have 3 quarters, I have 75 cents. So the third quarter is the 75th percentile. And that's all we're talking about. Incidentally, the 2 quarters, the 2 quarters, the 50th percentile, Q2, this is another name for the median. That's just the middle. So the first quartile, that refers to being 1 quarter of the way through the data. The second quartile, that's 2 quarters or halfway through the data. As we talked about, that's the median. And the third quartile as being 75%, or 3/4 of the way through the ordered data. And so these are just indicators of other positions that are kind of handy to know in terms of where data are ordered in the data set. So to find these, we do a formula. So this is our first kind of formula here. We take the percentile, either 25 or 75, depending on if you're doing Q1 or Q3, and you multiply that by n, the number of data points, and then you divide that by 100. So that equation is n times p divided by 100. And from here, we do the instructions of the median. So if we get a whole number, we do this and the one above. If we get an even number, we round it up, always round up, always round up. And then we just look at that position. So it's the same instructions of the median, but now instead of using n over 2, we use this slightly more complex formula in order to give us these extra percentiles. And actually, you can use this formula to find any percentile you want. This is the general position of a percentile formula, but we're just going to use them in this class for the 25th and 75th percentiles. Interestingly, for those of you who like math, if you plug in the 50th percentile for Q2, it reduces down to n divided by 2, the formula we used previously. Okay, everybody else who doesn't like math, you can stop closing your ears. All right, so again, if the solution is the decimal, round up always, and then that's the location. But if the solution is the whole number, just like before, with the median, then it's between that number and the one that's next up. So let's give this a shot. All right, so I'm going to have a data set, and I'm going to find Q1 and Q3 from it. So remember, the first step is still to order the data set. I put all of the data in order. Now I'm going to use the formula. Remember what I need for the formula. First of all, I need to know n. I need to know how many data points I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll make it easy. So I have 10 data points. And now I'm going to look at Q1 first. So Q1 is the 25th percentile. So I take that 25th, 25, put it in place of p, because that's the percentile I'm looking at. I take that 10 that I just counted out, the number of data points that I have, and I put that in place of n. Again, I just counted that out here. And I calculate that. I end up with 2.5, which rounds up to 3. And that is the position in the ordered data that the first quartile is. So again, I don't go to the original data set. I go to the ordered data set. Look at the 1, 2, 3rd position. That's number 7, and that's my first quartile. For the third quartile, I do the exact same thing, but notice what changes here. The biggest change is that my percentile is now 75th percentile instead of 25th percentile. So instead of just looking at the 25th percentile, I'm now looking at the 75th percentile in my equation and using that to calculate. By just making that one change, I get a different position in my data set. The position here is the 8th position for Q3. So I go to the 8th position in the ordered data set, 1, 2, 3, 4, 5, 6, 7, 8, and I find that 11 is the third quartile. Now you go on and give one a try. So find Q1 and Q3 from the below data set. So give this a shot. Go on and pause the video and come on back when you're ready. All right, so coming to this, again, first step is to order the data set. So put all of these values in order. I see that we have 1, 2, 3, 4, 5, 6, 7, 8 values in this one. So the calculations are going to be a little different. N is going to be 8. But note that for Q1, I'm always going to have 25 or 25 in the place of my percentile because Q1 represents the 25th percentile. Same thing with Q3. I'm always going to have 75 in place of that percentile. So those are going to stay the same. Here, if I do the, looks like my work here is skipping a step. So if I do the 25th percentile and 8, I end up getting the number 2. So 25th percentile times 8 divided by 100 gives me the number 2. And because it's an even number, I do this one plus the next one up, and I take the average of those two. In this case, it's 8 plus 9 divided by 2 gives me 8.5, just like with the median. So if you got stuck on this one, go on and pause it again to give Q3 a shot. But if you got this one right, don't need to pause again. We'll just keep going. But if you got stuck, go on, pause again. Give Q3 a shot now that you got it. So for Q3, I'm going to do the calculation. Again, it's 75 and 8. And looking at this, I get 6. So 1, 2, 3, 4, 5, 6. And because I got a whole number, I use this one and the next one up. That's what tells me the whole number is what tells me that I got to do that. This one and the next one up. So I'm going to take the mean of these two. 13 plus 13 divided by 2 is just 13. The mean of two 13s is just the number 13 itself. And that gives me Q3, my 75th percentile. All right, let's go to mode. So what's interesting about all of these is these actually go well with our levels of measurement. The mean is very good at going with ratio and interval levels of measurement. The median can actually be calculated with just ordinal levels of measurement. It's a really cool feature of the median, actually, that we can do the median with ordinal data. But for nominal data, we don't have anything that can work with nominal data yet. Enter the mode. So the mode is fantastic when working with categorical data because we can't do a mean or a median if we don't have an order. Recall, the median forces me to put things in order. So if I can't put anything in order, I can't calculate a median. So for the mode, we literally count up how many times each thing happens. And again, think about this in the context of categorical data. I have a whole bunch of people who told me their favorite color. How many people said red? How many people said green? How many people said blue? The value that occurs the most often is the mode. So if I say 87 people said red, 37 said green, 52 said blue, the mode is going to be red, the color. So one thing sometimes that students get confused on is that when we start kind of mixing frequencies with categorical data, they get confused between the number and the actual data value itself. So if I'm talking about favorite color and asking about a calculation of favorite color, the answer needs to be a color. So if I'm asking what's people's favorite color or what's the mode of people's favorite color, the answer should be a color. So when I'm asking mode of favorite color, if I tell you there's 87 people who said red, that should tell you how popular that value is. And you're looking for the number with the highest number of people who said that, the highest times that result occurred. But you're not looking at the number of times. The number 87 is not the answer. The answer is red. So what's your favorite superhero? We go around the class, we figure out, kind of put a tally under each superhero name, and then the superhero who the most people prefer, that is the mode. And we can have multiple modes. So let's say the same number of people, 80 people said red was their favorite color, 80 people said green was their favorite color, and that's more than any other color. Well, then red and green would both be the mode, and we can have multiple modes. I will say, if everyone said something different, I said green, you said red, somebody else said blue, somebody else said yellow, and there were no repeats, that is the only situation where we can have no mode. So if there's never a repeat, there's no mode. Otherwise, even if there's 100 repeats and they all tie, all of the ties are listed as the mode, as long as there's a repeat. Now, I will say mode is great for categorical data, but for numerical data, it doesn't make a lot of sense. So again, think about how many times each result occurs. Well, with numerical data, my numbers are, on a grade on a test, 97, 96, 95. And it doesn't really mean much to say how many times did an 82 occur on a test. On the other hand, if I have categorical data, categorized, or even ordinal data here, how many A's are on a test, that might mean something more. Why doesn't it mean much with numerical data? Well, because frankly, a lot of times there is no mode. There's just everybody had a different score, so no score is repeated more than once. There is no mode to calculate. But oftentimes, even if there's a mode, it'll be like 2 people in a class of 100 both got an 83.5. Like that just doesn't tell us much information. As opposed to, say, 30 people got an A, 40 people got a B, 15 people got a C, 10 got a D, and 5 got an F. That could be much more meaningful information. Again, with categorical data, it tends to be more useful than with numeric for the mode. Of course, with numeric data, we have medians and means, so we have more useful calculations in that direction too. That if we have numeric data, why would we use a mode when we can calculate a more specific measures of central tendency, measures in the middle? All right, so let's do an example. So we've got hospital visit classifications. I think this is NYU emergency department algorithm. Let's see, NEEM. Shoot, it's been a while. Oh, emergent, not emergent. Emergent and intermediate, I think, are the codes for these. Not emergent, emergent, and intermediate. So we're looking at the ED classifications of patients coming into the ED. Oh, I even say it here. I should have given myself one more bullet point. So looking at this, NE, not emergent, and EM, emergent, both occur more times than any other. So both NE and EM are in there 4 times. 1, 2, 3, 4 NEs, 1, 2, 3, 4 EMs. So both NE, not emergent, and EM are the mode. We have 2 modes in this data set. And again, that's okay. So literally, we just look at each of the options. In this case, there are 3 options, NE, EM, IN. And we see how many times did each occur. And whichever one occurred the most is the mode. And if there's a tie for the most, then everything that tied is considered the mode. All right, now you try this one. So we've got some blood types. Go on and pause the video and give this one a shot. What is the mode of the blood types for these 10 patients? All right, coming back to it. Looks like O occurs more time than anything else. Looks like A is in there 3 times, B is in there once, AB is in there 2 times, and O occurs 4 times. So because O occurs more times than any of the other blood types, O is the mode of that data set. All right, well, let's wrap it up here and talk about when do we use each of these. I've already kind of referenced when we use some of them as we talk about it, but sometimes it's nice to have it all on one slide to kind of wrap up our discussion of measures of central tendency. So the mean is a good default choice for continuous variables. It has some great theoretical properties. Again, it's this idea of a balance point of the data. Actually, it's the closest value to every point in the data. So if you calculate the distance between the mean and every point in the data, the mean is the closest one to all of them. So in that sense, it's got some really nice theoretical properties by being the closest single point to all of the other data points. The problem is again, if you think about that board, if I move something on the board, the mean necessarily shifts. So when there are things that push way, 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 way out, and if they keep pushing further and further out, the mean has to shift more and more and more and more towards them. And thus, when there's an outlier that is a data point on a very, very long board, so everything would fit on a relatively short board, but then there's a data point that's way, 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 way off there on a very long board. That's considered an outlier. With outliers, there's a lot of ways to approach them, assuming that they are not a typo or in some other way misentered. I had a case one time where I had a whole hospital of outliers. We were doing a study integrating data from a dozen hospitals, and one of the hospitals submitted data. We were doing height and weight. Everything was in inches for height and pounds for weight. And this hospital submitted their height and weight in meters and kilograms. And needless to say, They, if you send me a height of 2, and I'm looking at that as inches, that's a very, very, very short person. So we emailed them and had a conversation. So assuming those were all drastic outliers, once we got it figured out, we put them on the correct scale. Those are not data points that I'm talking about. So that's as long as it's not an outlier or a situation like that where it's on a different scale and you just have to convert it so all the numbers are on the same scale and representing the same thing in the variable. But that aside, outliers where there just genuinely is somebody who has a value that's very far away from the rest of the group, the mean is drastically shifted by that one individual. Sometimes that's a good thing, but sometimes that's not a good thing. So it's important to be aware that the mean is something that responds easily to that. It always responds to that. So for the median, it's a really good alternate choice for continuous variables. One thing that I love about the median is you can use it with ordinal data. You can't do the mean with ordinal data formally, but you can do the median without any problems at all. In fact, some of my favorite statistics are statistics that really rely on the median and use data that are ordinal. I really love that idea because, again, often ordinal data is kind of this weird stepchild in the analytics world. It's very difficult to deal with sometimes. So this median can be very useful for that. The other nice thing about the median is it is much better in the case of outliers. It functions much more cleanly. And again, think about that long board example. Well, if I move an item way, way, way out to the edge, the balance tipping point is going to move. But remember, median is the middle thing. So if I've got 5 things on my board, if I just move the end one way out, well, the middle thing hasn't moved at all. So my median doesn't move. The board's going to tip over and fall because the median's not the tipping point. The median's just the location of that middle item. So even if I not just moved one of them, but I moved the second item on that end way, way, way out, that middle item hasn't moved at all. So in the case of the median, you can have up to 50% of your data be massive outliers and the median not even budge. And that can be a fantastic thing for the median. Now, I will say, sometimes it's not good, but sometimes that can be a very, very, very attractive quality of the median, depending on what you're trying to express. One of my favorite classic examples is the income of history majors from University of North Carolina. The mean, and I think this is graduates in the 1980s or something like that, the mean is like $1 million a year or $100,000 a year or something like that. And the median is way less, maybe $30,000 a year. And the distinction is the mean shifts to accommodate Michael Jordan, and the median does not make that shift. So that distinction is actually really, really important in terms of what you're expressing. Now, it's important both ways because if you take out Michael Jordan, you've kind of missed that massive potential growth. So if that's something that you want to include in your measure of central tendency, then you should include that and you should use the mean. But if that's something that you're not trying to express, if you're just trying to express, well, what does the average person make? Oh, no, I'm not talking about Michael Jordan. I'm trying to say, like, what's your average run-of-the-mill person make? Maybe a median is a better expression of that quote-unquote average. That 50th percentile, that literal middle person, if they're all lined up, would be a better representation in that case. Again, it depends on the use and it depends on what you're trying to tell in terms of your story and what you're trying to communicate. So the interpretation is different for these two quantities. The mode is a good choice for categorical data. It's really the only choice for categorical data. Mode doesn't really tend to work well. It can work well with ordinal, but it doesn't really work well with interval or ratio. So mode is what we lean for with categorical data. And there's a ton of categorical data. It's really good to know. How many males versus females were in the study? What's the distribution of races? These are all mode questions. And frequency tables, which we use to calculate the mode. So those are all really good questions that we can ask of the mode. But again, it is primarily related to categorical data, not the other types of data options. Okay, well, this video has gotten rather long. I apologize about that, but this has been our dive into measures of central tendency, working through a couple of examples, actually getting to touch some data. In the next video in this lecture set, we're going to be discussing measures of variability or measures of spread. These calculations will actually get a little bit more intense, but they will be the most intense calculations and formulas we do in the class. So once you see them, the worst is over. Stick with me, and I'll see you in the next video.